Welcome all. In the last lecture, we have proved a formula or we have derived an explicit formula for the Cauchy problem of the non-homogeneous wave equation. Now it remains to verify the solution whether this explicit formula given by uxt is equal to f of x plus et plus f of x minus et by 2 plus 1 by 2c integral x minus et to x plus et g of s ds plus 1 by 2c double integral over the characteristic triangle delta f of theta tau d theta d tau is the solution of the corresponding Cauchy problem for the non-homogeneous wave equation. Now it remains to prove the verification part. Okay, for that that we will do in this lecture. Okay, we know that by the superposition principle, it follows that the solution uxt, uxt given by this equation, let this be equation number 2, and the Cauchy problem be equation number 1. Then the solution uxt given by equation number 2 is a solution of the Cauchy problem 1 if and only if the function if and only if this function which is in the equation number 2 including the double integral containing the double integral this function 1 by 2c double integral over delta f of theta tau d theta d tau is a solution of the Cauchy problem utt minus c square into uxx equal to f of xt where minus infinity less than x less than infinity t greater than 0 with the initial conditions u at x0 equal to 0 ut at x0 equal to 0. That means with the homogeneous initial conditions or initial data. So if this equation, if the function 1 by 2c double integral over delta f of theta d f of theta tau d theta d tau satisfies this equation 3 and 4, the PD 3 and 4, then obviously uxt given by equation number 2 will be a solution of the given problem with a non-homogeneous boundary initial data f of x and g of x given by equation number 1. This is because if this satisfies the condition at the homogeneous condition, that means for this function this x0 equal to 0, then obviously u at x0 will be this will be 0, isn't it? This will become 0 for this function at x0. This is 0, so u at x0 will be f of x plus f of x by 2 plus 1 by 2c x to x to x. That means this is again will be 0. So we will get u at x0 as f of x and g at x ut at x0 as g of x. Okay. So this will happen only if or u this solution u will satisfies the initial data u at x0 equal to f of x and ut at x0 equal to g of x if and only if this function which containing the double integral will satisfy the homogeneous initial data homogeneous boundary condition, that is u at x0 equal to 0 and ut at x0 equal to 0. So for convenience, we take the function as v at xt. So let v of xt is equal to 1 by 2c double integral over the characteristic triangle delta f of theta tau d theta d tau. Now we need to prove that this v is a solution. V is a solution of the problem 3 and 4. The Cauchy problem 3 and 4. Okay, so that we need to prove. Now, the characteristic triangle is given by, we know that the characteristic triangle is for the arbitrary point xt, that is with the upper vertex as xt. These are the characteristic triangle. Actually, let this be the okay. So here the variable of dummy variables or the variables are theta and tau. So let this be the theta axis and this be the tau axis. Horizontal axis is taken as theta and the vertical axis is taken as tau. Okay, so the characteristic triangle is this one with for the arbitrary point xt with xt as the upper vertex, and this will be the point x minus ct, and this is the point x plus ct. Okay, so this line is equation of this line. We know that for the arbitrary point, if the point is xt, and this will be theta plus ct is equal to x plus ct, and sorry, theta plus cto, since this is the C2 axis, we have the characteristic that passes through that that will touch the initial data at the point x plus ct if the arbitrary point is xt, and its equation, the characteristic equations are theta plus theta equal to x plus ct, and this line, equation of this line will be theta minus theta is equal to x minus ct. Okay, so these are the two equations, and this is the point xt, so this will be the point x0, and this will be the point okay, 0 t for tau. Okay, so here our function v of xt, we can write this as integral over characteristic triangle, that means integral over tau and integral over theta f of theta tau d theta d tau. Okay. Now the toe, the upper integral toe varies from, toe is the vertical axis. So toe varies from, we know that the integration is over this characteristic triangle. So toe varies from 0 to t. So 1 by 2c, we can write it as integral toe is equal to 0 to t. Now theta varies from okay, theta, here we are theta is the horizontal line, so the uh, integral is from this line, the line theta minus theta to equal to x minus ct to theta plus theta equal to x plus ct. So the integration starts from the line x theta minus ct is equal to theta minus theta equal to x minus ct, or theta is equal to x minus ct plus c2, or this is equal to x minus c into t minus tau. Okay, so theta varies from x minus c into t minus tau to the upper limit will be the second line, that is theta plus ct equal to x minus, sorry, x plus ct, or theta equal to x plus c into t minus tau. Okay, so this is x plus c into t minus tau f of theta tau d theta d tau. So these are the upper, lower and upper limits both for both the variables theta and tau. Okay, so this is about the function, or the function v of xt. So v of xt is equal to 1 by 2c, that is v of xt is equal to 1 by 2c into integral 0 to t and integral tau from 0 to t and integral theta from x minus c into t minus tau to x plus c into t minus tau f of theta tau d theta d tau. Okay. Now we shall prove that this is a solution. V is a solution of the Cauchy problem given by three equations 3 and 4 under the assumption that we assume that both the functions f and fx are continuous. So under this assumption we will prove that So we assume this one and we'll prove that V of xt is a solution of the problem 3. We satisfying the initial conditions, homogeneous boundary conditions. And for t equal to 0, it is clear that the first it is satisfies the first homogeneous condition v at x 0. What will be v at x 0? By definition itself, x 0 means t is equal to 0. So here when this equal to 0, the first integral becomes 2 varies from 0 to 0, like that it will get. So this will be equal to 0. So obviously or very clearly is clear. So we need to prove this only. What? We need to prove um, the second condition only, that is Vt at x0 is equal to 0. That we need to prove that one. Okay. Now, in order to take the derivatives, we use the Leibniz rule. That is Leibniz formula. That is dou by dou t of integral a of t to b of t, g of theta t d theta is equal to integral a of t to b of t dou by dou t of g of theta t d theta plus g of first theta is replaced by b of t comma t into b dash t minus g of a of t comma t into a dash t. So in order to find the derivative Vt at xt, we may use this formula, and we know that V of xt is a double integral function which is in the variable theta and tau. So first of all, we may consider the inner integral, the function g as the inner integral, that is theta integral over theta from x minus c into t minus tau to x plus c into t minus tau f of theta tau d theta as another function, that is g. So when we integrate this function with respect to theta, we will get it as a function of tau and t itself. Okay, so we can consider it as, or we can rename this as, let g of tau comma t, isn't it? Theta will be replaced. See, when we integrate this, we will get it as a function of tau and t. So g of t tau is equal to integral x minus c into t minus tau to x plus c into t minus tau to f of theta um, tau f of theta tau d theta. Okay, so we rename this as g of tau t. Therefore, v of xt will be, therefore v of xt is 1 by 2c into integral over tau varies from 0 to t, tau varies from 0 to t, g of tau t d tau. So we can have g and v as these functions. Okay. Now in order to find vt, therefore vt at xt will be 1 by 2c is constant, dou by dou t of integral 0 to t g of tau comma t, g of tau t d tau. Okay, so here we can apply the Leibniz rule for Leibniz formula for finding the derivative. Okay, so for finding this derivative by the Leibniz rule that we have already written here, that is this one. This is the Leibniz rule. So this is the Leibniz rule. So here a of t is the function. Here a of t is equal to 0 and b of t equal to t, and g is instead of theta here we have tau, and t is the same variable. Okay, so by the Leibniz rule we can apply here. This is equal to 1 by 2c into integral over 0 to t dou by dou t of g. First is given dou by dou t of g of tau comma t d tau. Okay, d tau plus 1 by 2c is in bracket plus g of b of t comma instead of tau we have to apply first upper limit, that is g of t comma t into derivative of t, that is 1, plus g of 0 comma t into derivative of 0, that is 0. Okay, so by Leibniz rule we have this one, so which is equal to 1 by 2c into integral over 0 to t dou by dou t of g of tau comma t d tau plus g of t comma t, like this. We will obtain like this. So this is equal to 1 by 2c into in bracket integral 0 to t dou by dou t of g of tau comma t. G of tau comma t is integral x minus c into t minus tau to x plus c into t minus tau to f of theta tau d theta, f of theta tau d theta. So d dou by dou t of this one into d tau. Okay, so this is under integral 0 to t plus g of t comma t. G of tau t is this integral. So g of uh, t comma t. That means instead of tau we have to apply what? We have to apply t itself. So substituting t is equal to tau is equal to t. We have that will become tau is equal to t. So integral x to x, isn't it? Yeah, integral x to x minus c into t minus t will come. So both the integrals that will become 0. So integral x to x f of theta t d theta will come. So this is again integral x to x, and we know integral x to x is 0. So this will become 0. And here we have to, in order to apply this, in order to find the derivative dou by dou t of this integral, again we have to apply the what Leibniz rule once again. This is equal to 1 by 2c integral 0 to t dou by dou t of integral um, x minus c into t minus tau to x plus c into t minus tau to f of theta tau d theta in bracket into d tau. Okay. Now applying the Leibniz rule, Leibniz formula, we have 1 by 2c integral 0 to t. Now applying the Leibniz formula, this will become integral x minus c into t minus tau x plus c into t minus tau into okay dou t of what, f of theta tau dou by dou t of d theta tau into d theta. Okay, plus now f of theta is replaced first by the upper limit. So x plus c into t minus tau, comma, f of theta tau. So tau into derivative of the upper limit. Derivative of x plus c into t minus tau. Dou by dou t of x plus c into t minus tau, that is c, uh, minus f of, now replace theta by the lower limit x minus c into t minus tau, um, comma tau, into derivative of this lower limit, that is minus c. Okay, so this in bracket into d tau. Okay, so again this is equal to 1 by 2c integral 0 to t. Here the first integral, and in the function under the integral sign, dou by dou t of f of theta tau. F of theta tau means f is a function of theta and tau, and here we are differentiating with respect to t, so that will be 0. So inside the integral, that will be 0. So this will be 0 plus c into c, we can in both the terms, both the remaining both terms contain c, so we can take c outside. C into capital F of x plus c into t minus tau, minus comma f of x comma c plus t minus tau comma tau, plus f of x minus c into t minus tau comma tau. Okay, into d tau. So this comes, this will be like this. Okay, again this is equal to, we can take this all in bracket. This is in square bracket. Okay, 1 by 2c into, we can take c outside. So c get cancelled. 1 by 2 into integral 0 to t f of x plus c into t minus tau, comma tau, minus f of x minus c into t minus tau, comma tau, d tau. So this about the d tau. So this is vt at xt. Okay, integral 0 to t. And then clearly we have, therefore in particular, or clearly, vt at x0, when t is equal to 0, we will get integral from 0 to 0, that means it's equal to 0. So we have proved that v satisfies both the initial conditions, that is v at x0 is 0 and vt at x0 is equal to 0. Thus we have proved that v satisfies the uh, equation 4, that is the initial conditions given by equation number 4. Now we need to prove that V satisfies the PDE given by equation number 3. For that we need to find VTT and VXX. For that we have obtained, now we have obtained VT, isn't it? VT at XT we know. Now in order to find VTT, so to find VTT, we have to once again differentiate this function, that is given by, let this be equation number 5. So we have to differentiate 5, that is again we have to apply the Leibnitz formula. So for that our new function g of tau t, we can define this as g of tau t as f of x plus c into t minus tau, comma tau minus f of x minus c into t minus tau, comma tau. So this is our new function g. and okay, this is our g. Therefore vtt at xt will be dou by dou t of uh, 1 by 2 into dou by dou t of integral 0 to t uh, g of tau comma t d tau. Okay, equal to 1 by 2 into by Leibniz formula we have integral 0 to t dou by dou t of g of tau comma t into d tau plus g of t comma t into um, derivative of t, that is 1, plus g of 0 comma t into 0, which is equal to 1 by 2 into integral 0 to t dou by dou t of g of tau comma t. By definition it is f of x plus c into t minus tau comma tau minus f of x minus c into t minus tau comma tau into d tau plus g of t comma t. G of t comma t is replace tau by t. So this will be f of x comma t uh, so actually this is not minus, this will be plus. Okay, this is plus. Here also it is plus. Okay, this is also plus. Okay, then f of x plus x t plus again f of x t, tau is replaced by t into, so this into 1 plus again 0, that is we have f of xt plus f of xt is 2 into f of xt by 2, so it will be f of x comma t plus 1 by 2 into integral 0 to t integral 0 to t dou by dou t of f of x plus c into t minus tau comma tau plus f of x minus c into t minus tau comma tau into d tau into d tau. So this we have to calculate. We have to calculate this dou by dou t of this one. Now for convenience we may take uh, x plus c into t minus tau as y, another variable y, and x minus c into t minus tau as another variable z. Then this can be reduced as written as f of xt plus 1 by 2 integral 0 to t dou by dou t of f of y comma tau plus f of z comma tau into d tau. Okay, where where y is equal to x plus c into t minus tau and z is equal to x minus c into t minus tau. So this is equal to, then now we can apply the chain rule. So this is equal to x f of xt plus 1 by 2 into integral 0 to t dou by dou t of f of yz, we can write it as by chain rule dou by dou y of f of yz into dou y by dou t plus dou by dou z of f of zt t is it tau into dou z by dou t. This into d tau, which is again equal to f of x t, f of x comma t plus 1 by 2 integral 0 to t. Now dou by dou y of f of yz into dou y by dou t. Dou y by dou t is by dou by dou t. Y is equal to x plus c into t minus 2 tau. So dou y by dou t will be c and dou z by dou t will be minus c. So this is equal to dou by dou y of f of yz into c plus dou by dou z of f of z tau z dou y tau, not yz, y tau. This is also tau into f of z tau into minus c. Now we can take the c outside. So this will be f of xt plus c by 2 integral 0 to t. This will be c we can take on outside. So this there will be minus sign. So this into d tau. Okay. So we will get like this. Now we can rewrite this as f of xt plus c by 2 into integral 0 to t. Now dou by dou y of f of y tau can be written as dou by dou x of mm, f of dou by dou x of f of x plus c into f of x plus c into t minus tau comma tau and dou by dou z of f of z comma tau can be written as dou by dou x of f of x minus c into t minus tau comma tau into d tau. This is possible because this instead of this we have written like this, and instead of dou by dou z we have written like this. This is because we have dou by dou x of f of x plus c into t minus tau in t minus tau comma tau is equal to, we can write it as dou by dou x of f of some y comma tau for y equal to x plus c into t minus tau. Okay, so by chain rule we can write it as dou by dou y of f into dou y by dou x plus dou by dou tau of f into dou tau by dou x. Okay, so this is equal to dou by dou y of f of y comma tau into dou y by dou x is 1 plus dou f by dou tau into dou tau by dou x. Dou tau by dou x we know it is equal to 0. Okay, so this will be equal to dou by dou y of f of y comma tau. So instead of dou by dou y of f of y comma tau, we can write dou by dou x of f of x plus c into t minus tau comma tau. Similarly, uh, we can have dou by dou x of f of x minus c into t minus tau comma tau is equal to dou by dou z of f of z comma tau. So thus we have obtained this equation, that is we were calculating VTT at xt. So VTT of x comma t we have obtained like this. Okay, then now again this can be written as this VTT at xt is equal to f of xt plus c by 2 integral 0 to t dou by dou x of f means fx of x plus c into t minus tau comma tau minus fx of x minus c into t minus tau comma tau into d tau. And similarly we have, so this is Vt, and similarly we have Vx at xt is equal to 1 by 2c integral 0 to t f of x plus c into t minus tau comma tau minus f of x minus c into t minus tau comma tau into d tau. Therefore, Vxx at xt is equal to 1 by 2c into integral 0 to t fx of x plus c into t minus tau comma tau minus fx of x minus c into t minus tau comma tau into d tau. Thus we have Vxx and Vtt given by equation number 6, and let this be equation number 7. Okay, so c square into Vxx will be given by c square into Vxx will be c square by 2c, that is c by 2 into integral 0 to t f of x fx at x plus c into t minus tau comma tau minus fx at x minus c into t minus tau comma tau into d tau. So compare this with the equation number 6. So this is actually the second term of the right side of equation number 6. So therefore we have from equation 6 from equation 6 we have Vtt is equal to f of xt plus c square into Vxx, or Vtt minus c square into Vxx equal to f of xt. Therefore, V satisfies the PDE given by equation number 3. So we have proved that V satisfies the PDE 3, and also the initial it satisfies the initial data, that is V at x0 is 0, and also Vt at x0 equal to 0. Okay, so V satisfies equation number 3 and 4. V satisfies these two equations. V is a solution of 3 and 4, and hence by the principle of superposition, U is a solution of the corresponding PDE given by equation number 1. So that's about the verification. Okay, thank you all.